We're going to begin by discussing the types of chemical bonds, and eventually we're going to be able to use the identification of materials to be able to draw chemical structures. So what are the three types of chemical bonds? Well, we're already familiar with ionic bonds, that is, bonds between elements, or ions we should say, that are held together through electrostatic interactions. That is, they're held together by the fact that positive and negative charges attract. The second type of bond is a covalent bond, which involves the sharing of electrons between two different elements, namely nonmetals. The third type of bond is known as a metallic bond, and it can be found in something like iron or nickel or gold, some sort of metal or a combination of metals. And this involves the electrons behaving like a gigantic sea, where the electrons are free to roam around the metals and have no real constraints on where they can go. So let's talk about ionic bonds first. As we saw in the previous chapter, it takes energy to remove an electron from something that forms a cation. For example, it takes 496 kilojoules of energy to ionize sodium into the sodium +1 ion. Likewise, we saw that adding an electron to an atom, resulting in an anion, always releases energy. So putting in something like an electron into chloride, we get 349 kilojoules of energy back, or released in the form of heat. But ionization and electron affinity don't explain why ionic bonds form. We need another component here. If we put sodium metal and chlorine gas in a canister, we will form sodium chloride, and it is a highly exothermic reaction. Yet if we go back and add the ionization of sodium to that of chloride, we find that it's an uphill battle. So what is causing this reaction to go, and why is it so exothermic? Well, this has to do with the idea that the sodium ion's electron the sodium ion is going to transfer an electron to chloride, and that the fact that you now have a positive and negatively charged particle sitting next to each other is going to cause them to attract to make sodium chloride or salt. Now, this attraction of positive and negative charge is known as lattice energy. That is the energy required to completely remove these two charged particles together. It's going to take energy to remove the particles, which means that it releases energy when these two charged particles find each other. And we call this lattice energy, we base it off of Coulomb's law. That is, the energy is equal to some constant kappa times the two charges of the cation and the anion divided by the distance or the bond length they're separated. And what we can find is that the lattice energy provides more than enough energy to compensate for both the uphill process of the ionization of the cation as well as the lack of energy released by the formation of the anion. Lattice energy is the key concept here to the formation of ionic compounds. So what dictates lattice energy? Well, again, the magnitude of the charge of the ions, that is, the higher the charge, +1, +2, +3, the greater the lattice energy is going to be. The other component is the distance that the two ions are separated, and that is the bond length. And when trying to prioritize which one's more important, obviously the charge is going to be the more important factor because of the magnitude of the numerator. So we can see here that there are a series of different chemicals, for example, lithium fluoride, lithium chloride, lithium iodide. And what we find is that as the size of the anion increases with these lithium compounds, the lattice energy decreases because the distance between the two nuclei is getting bigger and bigger and bigger, and that has a diminishing effect on the lattice energy.